Okay, the recording is started. You will see a button sometimes, red button on your side. Let me share my screen now. Okay. Okay. Can you see my screen?
Yes.
Okay, very good. Again, please keep yourself on mute, so that there's no background noise, and so that it's easy for everybody to hear and everything. Okay. All right. So my name is Dipankar Medhi, and I go by Deep Medhi, very short name. And I grew up in Assam. I was born in Guwahati, and I went to Cotton College at higher secondary school. Matriculation exam. I did then study 11 and 12 in Cotton College, and then BSc mathematics from Cotton College as well. Then I went to University of Delhi, where I did my master's in mathematics, and then I came to the United States. I went to University of Wisconsin at Madison, where I did PhD in computer science. After my PhD, I did work in industry for R&D for 2 years at AT&T Bell Laboratories. And so that's a long time ago. I came to the US in 1983. So it is 37 years now. And so I've been a professor at the University of Missouri at Kansas City since 1989. And then 2 years ago, I joined the National Science Foundation in the US, and where I'm a program director. And I plan to do a series of presentations over the next, few months, actually, with a gap of 3 to 4 weeks. And if you signed up on my WhatsApp group, I'm going to announce the future date for any of those sort of a webinar for you on different topics of interest, and which I have not quite formulated yet, but I kind of know what I'm going to do the second one and the third one right now. So let me start with that without any delay, and hopefully you can hear me and everything. So interdisciplinary science. So what I'm going to say, I'm going to connect it between physics, computer science, statistics, and how computer networking plays a role there. So let me see. Okay. All right. So here is a picture I wanted to show you from the moon landing 51 years ago. That was just exactly a few days more than 51 years ago. Very exciting time. I remember as a little kid about the moon landing. And so the science has progressed a lot in terms of what we have done. We have now, space station where, we send astronauts and they stay there for some time and then come back. But to me, the space is always very, very interesting. And I got interested when I was young and got to know about the moon landing. But I'm not a physicist. I want to make it clear. My background in mathematics, as I said at the beginning, and then I did computer science and computer networking. But I've been very interested in how different things can be connected between different sciences. So I like to say this quote is one of my favorite quotes from Isaac Newton. If I have seen farther, it is by standing on the shoulders of giants. And to me, by giant doesn't necessarily mean all the scientists. It means many people I have come across in my life, from my parents, my family, my aunts and uncles, my friends, and my students, and you, when you will ask me a question. I ran this session a few days ago. There were fantastic questions that people asked, and it made me think about a few things about it, right? So I want to start with giving a specific credit in terms of 3 people who really helped me with answering some questions I had, and especially material. Katie Bauman, she is at California Institute of Technology, and she allowed me to use some of her slides. She was said that please go ahead and use my slides, no problem. And I try to credit her on the slides. She has given the content to me. Similarly, Harvey Newman and Frank Wertwein, you know. And so on some of the slides, you will see their names, one of their names, but the ones that's not anybody's name, that's usually I have put it together. And I try to give credit to the source where I got different things, including graphs and whatnot. It's very important to remember in science to give credit to what others have done and continue to do so. So let's start with a joke. I like to take jokes. And if some of you who listened to it last time and probably heard it, but I'm going to tell it again. So this is a joke about when Pythagoras met Einstein, you know, what happened when they met. Of course, they didn't live at the same time. You know, Pythagoras goes to the Greek time frame a long time ago. And so let's start with Einstein's famous equation or formula, which is many of you know, even if you are not in sciences, called E equal to mc squared. And is very well known. About 100 years back, Einstein came up with this result, right? And so, and then we know about an interesting result from Pythagoras. We learned it in school, in high school. And what is that one? That one is known as the Pythagorean theorem, which says a squared plus b squared equal to c squared. And you know, what is that? This is about the triangle with a right angle triangle. The two sides of the triangle, when you do the square of those two sides, it is to the third, the longer side of the triangle, which is opposite to the 90-degree angle of the triangle, right? So the thing is that I found this picture recently, and it's actually a face mask somebody printed. I'm going to order it. It just says that a square plus b square with a dot 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 equal to m with a dot dot dot, and you see two people fighting over the c square. One is Pythagoras, who actually had the c square in his formula, and Einstein, who also had the c square in his formula. Okay, they are fighting over it because Pythagoras said it c square belonged to me, and Einstein said it belonged to me now. Obviously, the meaning of c square is different. And so what happened, eventually they settled on it, and they'd come up with a new formula called a squared plus b squared equal to e over m. And it's a simple algebra substitution. That's the joke about the whole thing. Okay, so let's start with where we want to go, and I'm going to keep track of time. Let's start with the black hole image. So black hole image, the picture first came out in April of 2019, little over a year ago. And many of you have seen it on maybe TV, and maybe even got printed in a newspaper. It was a big, very, very big news. In fact, National Science Foundation did a lot of the funding for the Event Horizon telescope that allowed this picture to be taken. So the mystery starts with being able to, you know, sort of going backward now, that if we have this image, what made it allow to happen, and a couple of other things then I'll talk about. So first, there's a small animation that Katie Bauman gave it to me about with the black hole. You don't need to know anything about black hole, the basic, except that black hole is the idea when the stars collapse, when they lose their power. Think about sun always losing power. Over time, it's going to lose more and more power. What happens with the gravitational forces and the light and whatnot. So if let me see my animation, I'll let it run it by itself. So light actually kind of, you can see what is going on with there. It takes a curve there, everything, and then you are going to turn it around this image. And now you can see the view that around the black hole, you can see those kind of crossing the lights around it point. And then if you then take like a two-dimensional view from away, you are going to get the black hole in the middle and the lights around it, like exactly like this picture, okay? So that's what you're trying to actually accomplish with a black hole with a shadow around it, right? So then, if you actually think about it, that was just a one instance of the picture. But remember, there constantly something is happening. So if you really want to take a dynamic picture of or what it is going on, you are actually going to get like almost like a movie of what it is going on with there, and trying to get picture of that one. So this is just like a short animation of the black hole simulation, what it's going to look like and whatnot. So then eventually you get this picture. So you can see the picture is actually blurry. There are many reasons for it. I'm going to talk through some of them, why the picture is blurry. So it is not going to be perfect like the initial picture I showed you with the black hole and all the lights around it, but it's going to be fuzzy around it. And there are many reasons for it, and I'm going to talk through that as we go through this part. Here's a picture of the people who actually, it's a small, sorry, the group is big, only a subset of the people were in this picture who contributed to taking the image of the black hole. And they are all associated with what is called the Event Horizon Telescope. So what I want to do is that, let's take a step back. Basically, black hole is an image. So let's think about how we take an image or a picture. So we start with the simplest thing that we know about, the camera, right? So what do we do with the camera? That we can take a picture of a person or on a desk or a mountain, whatever, and we can actually capture it, what we did. The reason we can capture is because the aperture of the camera, because it can see the whole piece of it, and you can actually take a picture of that. The other important thing to note is that even the best digital camera, whatever the image you get, is actually an approximation. And you have probably seen there your friend's mobile phone and your mobile phone, you compare, take the same picture, it looks different. And there is a reason, because the approximation that is done with the digitizing the image from the information that is captured actually changes a lot with this, changes a lot in terms of depending on what the mechanism it is used. Another way you can say that in the old days with analog camera, we take a black and white picture, that's actually an approximation because we are in color, right? As a human being, or what is our surrounds us. So, so you have to keep in mind that there's an approximation. The question is how close to the reality we can approximate something. So let's look at this traditional picture with a camera. This is a digital picture. You can see the picture. We're assuming the picture on the left is actually the reality. It may not be exactly reality. It may depend on the light and how you change all the imaging focus nowadays. You can do with fancy photo tools and stuff like that. And here's actually a picture with this camera. Maybe you got a picture look like, it sort of looks blurry, and blurry could be for a variety of different reasons. So here, because you are using this is a picture with a DSLR camera, what you can see is the DSLR camera only focuses on this, this particular one on this flower, the color, the purple color, and the rest of it is purposefully blurry. That's how DSLR works. But as a human being, we see closer to what's on the left side. So you already know the idea of an approximation, what it means when you try to use a camera and stuff like that. So then the question is that how can we use, take a picture of a black hole with a camera? So the camera we can then think about is to think of in terms of a telescope. So telescope, when you think about you and I, we think about a telescope as something we can put it and just look it out on the sky, we see something, you know, yes, but you can make it's bigger and bigger. So that goes to the idea of the aperture. So the question is, how big of a telescope do you need, right? So here is the big formula from astronomy that is very, very important. This basically says the size of a telescope, by size I mean the diameter of a telescope, is equal to 1.22 times the wavelength of the signal and the angular resolution, right? So when you think about in the context of what we are looking at, taking a picture of a black hole, and let's look at some of the values. So what happened is that the value of the angular resolution is 20 micro arc second. So what is the 20 micro arc second? You can see it up in the formula, the value at the top. It's a 5.56, then 10 to the power negative 9 degree. So remember the 90 degree angle I talked about, you know what a 90 degree is, right? So it is 10 to the power negative 9, it's a really, really tiny angle, very small angle we're thinking about, right? That's what a micro arc second goes about. What about wavelength? Wavelength happens to be 1.3. So if you then try to calculate the diameter, comes out to be 13 million meters. So if you look at how big is a 13 million meters, it's roughly going to be that I need something in the size of an Earth to be able to take a picture. So you want to take a picture of the M87 image, which is the black hole. You need a size of the Earth to be able to take a picture. So you need a telescope of that big. Obviously, we cannot build a telescope that big. So what we do is that we do approximation. So a very interesting thing about, I will keep using the word approximations and errors and stuff as we talk through it. Here is what they did. You can see that they actually purposefully positioned telescope at different places. You can see a telescope at South Pole. This one is in Spain, IM telescope. This one, ALMA, is in Chile in South America, very famous one, on the top of the mountains. Then Maxwell telescope in Hawaii. There are two telescopes there. Here is one in Mexico, and this one is Arizona. So you got this set of telescope. Then what they use, what is called the very large baseline interferometry. So VLBI, it's an arrow of small telescope trying to mimic the size of the diameter of the Earth so that we can take a picture of the black hole. And so what they did, that they figured out 10 days in April 2017, almost 3 years ago. And luckily they got clear weather for 4 days of that 10 days and to take pictures. And then what they did was that they clock synchronized all the telescope to atomic clock to GPS synchronized to take pictures, clicking a picture exactly at the same time, almost like, right? And the time is very important here because the picture was taken in April 2017. And remember the black hole image I talked about at the beginning, it was actually came out in April 2019. So it took them 2 years from the collecting the data to be able to create an image like that. And the thing that went through to make it happen. So here's what it means is a look at the Earth is always moving. That's a very interesting. I'm trying to take a picture of something when the Earth is moving. You can see the satellites and it's taking picture, and it's marking on the right when it is taking a picture between which one it is taking. It is kind of coordinated between different points there. It's repeating the same thing again so that you can see that this animation again. So you can see the blue, then the green, then the yellow that is coming. So we're trying to take a picture and a purple, and it's going to take a picture. And you can see that when it is trying to take a picture, you can realize that it's actually not being able to capture all of the information within this two circles. So assume that the inner circle is actually the black hole, the outer circle is your, the lights that you wanted to capture. Make sense? And you can see that there's no way, even with having this number of telescope in six or eight places, I can actually take so that means I get a sparse amount of information. So almost like I get something fuzzy information. The question is, how can I make it into something more manageable and workable from there, right? So this is where what I have to think of. So what happens, we cannot see a picture. We don't know what it looks like. So you have to basically sense the system, measure it, take account of the error, and you use algorithm. It comes from computer science, and then you reconstruct the picture. So that's sort of what happened with this one, with that part of it. And so, so unconventional image, basically, if you look at it that way, a simple way to think about the whole idea, there is the true image. This is where the satellites are. And you do the sparse measurement. You saw this thing. You do some magic with the algorithm, and you actually want to reconstruct the picture. That's the whole idea. The vision is always important in science, that you want to do something, see something, and how you want to actually accomplish it. So now I'm going to switch gear to a different thing called the Large Hadron Collider. So Large Hadron Collider is very, very important. And that one basically is that we are trying to figure out about dark matters and dark energy and whatnot. So what they said, the universe is 67% is dark energy, 29% dark matter. Only less than 5% is actually atom. That's what we are, on Earth that we see. That means we are not seeing a lot of things that's out in the space there. So how can we actually find that information? So it became a big challenge. And so to try to, so there's some basic idea about this goes back to 100 years ago. So what they came up with that to actually figure out about studying the dark matter, you actually need a very large ring. And it's actually in Europe that they place it. And so they're going to then, not only that, there are multiple reasons for having this large ring. You can see they have marked it CMS, Atlas, Alice, LSCB, and all of these things. The 2-3 things are purposefully they are apart so that one signal collected at one point is not going to interfere with another signal collected at another one. So distance matters, right? And secondly is that these are two different group of independent scientists. The group means that it's not 1 or 2 or 3 people. It's hundreds of scientists on one group, another group of scientists in another group. So because you want to say that what you observe on one side, you are being able to also observe on the other side. Only then you have a confidence with the information. It's not that, after doing all the calculation and stuff. So this is where this is a picture of inside of, you can see how big it is and inside of the human being standing next to it and whatnot. And so the Large Hadron Collider is 27 kilometers in circumference. You can collide this many protons at the energy. And you can see the beam size for what they do, and more than one collision per beam crossing and all this stuff, they have actually set it up. So a lot of investment and cost into trying to figure out about the dark matter. So this goes to a little bit of a history here, science history. So it's actually it actually goes back to Bose-Einstein statistics we talked about from 100 years ago. So it turned out not Bose who actually came up with some ideas about it. And then in 1964, the theory that there is another particle got discovery, high energy frontier Higgs boson that we want to be able to actually possible that we do not know, but we believe it is there. It is written is 48, and from 1964. Then in 1984, they conceptualized the Large Hadron Collider. Construction started in 2001. It ended in 2009. And 2012, they actually discovered, really observed it using the circular, LSC that I talked about. And then a year later, Higgs was still alive, wrote the paper in 64, and Englert, they actually got the Nobel Prize because it was actually finally proved. It is no longer in theory. So going from theory to practice sometimes take a long time. And, and then from practice to something making practical is maybe even take a long time. So I'll give you a quick example. Many of you have or heard about fiber optics. A lot of internet data go on fiber optics. It's all about light traveling, right? So the fiber optic idea, we know about light for a long time, but the fiber optic, how to construct it and, and whatnot, the basic things in physics happened probably 50, 60 years ago. The person actually got Nobel Prize for that work. But from that to make it product, another 20, 30 years to make it a product. Now, large amount of data on the internet goes over actually optical fiber. So what else about LHC? So what I did, remember I mentioned about Harvey Newman, who I got to know. So I asked him that question that what else do we want to do with, so I'm going to put those 3 things so that, and there are a lot of words in there, and I'm going to kind of quickly pass through it and go through it and without reading each of the items there. So first thing is that we're still searching for more fundamental theory of nature, very, very important, beyond what we know. Second thing is that the standard models that we talk about, no place for dark matter particles. So we wanted to know, so we also do not know what dark matter is. That's really the next thing that we want to be able to know beyond what we did with the Higgs boson, the discovery that it is, right? And that's where you want to be able to do. So then my other friend, Frank, I asked the same question in a slightly differently. He says that why do we need the LHC, the Large Hadron Collider? He said that the problem is that particle smashers like LHCs, it generates lots of different things. And the thing is that when it produces a lot of different things, you know, it's like all your atomic particle that we know about, right? It already can, depending on how you break it and whatnot, we know the atom, the molecule, and whatnot. So what happened is that it actually generates lot of data, but a lot of this data is actually is not very interesting because previous generations have actually found it. That's basically, think about like the atomic particles we know in the last 100, 150 years, right? Starting with hydrogen, oxygen, and whatnot. But what he said that we need to really measure very, very rare collisions. So that means we need to throw out all the things, and to measure rare collisions, what we need is a very bright, we did very bright beams, okay? It produces bright beam, but what he said is it produces unbelievable amount of data. I said that how much data? And I said that, Frank, you said data, how much data did it produce? So this is where let's visit at how much data it is produced with black hole imaging for Event Horizon Telescope, and with also with Large Hadron Collider. Because so far I haven't talked about how much data it is. So here is Katie Bauman, who actually provided some of the animation I showed you earlier. And Katie, here is a picture of Katie with a hard drive of all the tapes that was collecting the data to be able to create the picture. And what it says that all of the data together from the VLBI, the voltage signal data they collected, it came out to be 5 petabytes. So the question is, how big is 5 petabytes, right? So 5 petabytes, just to give you a context, I put a few numbers there that we're familiar with. So of course, our basic units is 1 byte, and then you go to 1000 byte makes it 1 kilobyte. Then you go to 1000 kilobyte to 1 megabyte. So most of your camera pictures that's are in the megabyte time frame, megabytes time size on the lower end, depending on the type of the camera, maybe 1 meg, somewhere in 5 to 8 meg pictures you can take. If you have a DSLR camera that I talked about earlier, you can get images of 30 meg if you especially save it in raw image, which is what I like to do with images. Then 1000 megabyte makes it gigabyte, and 1000 gigabyte makes it 1 terabyte. So nowadays a computer hard drive is between typically 100 gigabytes to 4 terabytes, okay? And so please mute yourself. So. Excuse me. All right, so what I want to quickly say that that's actually 10 to the power 15, but most interesting thing, I talk about Apollo 11, the memory on Apollo 11 was only 32 kilobytes. So it amazed me that with that much of little memory that they could actually send a craft, you know, rocket to the moon and bring it back. It's incredible. So it's what they were being able to do to make that happen is unbelievable. So, okay, so you got an idea about this, what 1 petabyte is 10 to the power 15. And so Dan Marone made a very interesting comment. He said that it's equivalent to 5,000 years worth of MP3 files. MP3 is what? Your music files are, you know, you cannot imagine how big that is, right? And or it is the selfie collection, you know, all of you like to take, me too, like to take selfies, and a lifetime of 40,000 people. So even the room, here, how many people are? About 50 people attending right now. And so, you know, we're not going to generate this much of data at all, right? Very small amount of data. It's amazing how much data we have to generate. So now let me look at the Large Hadron Collider. It is, you can see the numbers about they generate 10 petabytes of raw data per year, written into tape, not counting simulation, you know, important of information they do it, you know, they do some filtering, all kinds of stuff they do, you know, because they're only interested in certain information, not everything. So again, asked Frank to give some context to all the things. He said that for one of the experiment on the LHC that I talked about, the collider, one group, they do, it's like if your camera is 100-megapixel camera, and as if it is taking a picture every 25 nanoseconds. So that kind of gives you an idea about what it is happening and what not. And even with that, you are actually approximating, because you are not sure when you are going to get information about something related to something like Higgs boson, or next thing we wanted to know about that. So where is now that the computer science, statistics, and all this stuff, networking come into the picture? The first thing you realize that from the last few slides, that I actually talk about data. Not only that's a lot of data. Second thing, I talked about error in measurement and the sparsity. Remember the when the artist rotating the picture and it's taking the snapshot with those telescope, we are actually only capturing only part of it. We're measuring it only sparse information, not being able to take the picture of the whole black hole, but we want to be able to as much we collect, but at least do a good approximation of what it is going to look like. This is where the statistics become very important. When you do measure, you have a sparsity of data, you have error in your measurement potentially, then you need to have statistical technique and statistical confidence way to be able to say, you know, to make actually that you actually have believe in the result that you actually saw it, right? Scientifically believe it. So for science, this depends a lot on statistics because of that. And not only physics, but other sciences as well. So then the question, how do you move around and how to reach where the data are? You know, if you have 5 petabyte of data, that's a lot of data that you want to be able to access and whatnot. So you are kind of saying that, okay, fine. So what this means is that going back to talking about the black hole, we need to develop new computer vision algorithm that works with noisy and sparse data, very important. And I already talked about statistical methodology. So let me give you an image, imaging a black hole, what actually happened. So what I find out is that there are actually a bunch of different sources of errors. The first error is what is called, comes from the atmospheric error. That means the amplitude attenuation. That means any signal, you can represent it with those who have learned a little bit of signal, you can represent with the sine curve. Sine curve you're familiar with. And amplitude, basically, let me show you a small picture here. So he said this is a signal that is actually can be presented with this one. The amplitude means what's the highest value at the lowest value, and the two peaks at the on the top, it is called the period of this sine curve. So that goes to your 2 pi in a sine curve, because there's a 360 degrees. You are going it around. So let me see if I can show to explain the attenuation. Let me pick the color, a pen and a color. Attenuation means that because my signal is not good, I actually could not achieve the next time as high, did not receive as much like that. So that means if you get farther away, you are going to lose the amplitude of the picture. So you have to worry about that error that comes from the atmosphere in this particular case. Second one is the atmospheric error is what is called the unknown phase. The idea of a phase is, I'm going to show it again, another picture. So you have this original picture here, but if it gets shifted by a little bit because of the angular movement, that means that's the phase. So you said that what's the unknown phase is going to have, because you have to correct it back to be able to actually do the calculation, right? And then there's actually additional amplitude error they found out. So those are the things they have to actually take care of. So they came up with two classes of algorithm, two different group of scientists work on inventing new techniques to be able to do it. On the left side, basically they say that, okay, I got that picture. You have seen this before. When I say the word reconstruct, what is the meaning of a reconstruct? To reconstruct is basically mathematically means if you're taking an inverse of a function. So what is an idea of a function, right? So if you say a function is equal to y equal to, let me see how good I am at writing backwards. So let's say I have y equal to x squared. This is a known function, closed form function we call it, right? So if I want to take an inverse, what is going to be doing is going to be x equal to what? plus minus, I'm not going to write the plus minus, square root of y, right? That's your f inverse of y to get it back. Because this function, I know the function to start with mathematically, I can do it. Here, this function is not a closed form function. That's part of the difficulty. So you have to do a lot of different ways to be able to figure it out to get back to something like that. The second group of people actually on the right, they look at it from a statistical methodology point of view. That how do I look at that information? Do I have a confidence? Do you do Bayesian statistics and whatnot? They use it, and I think I have pictures. You can see all of the noise that I talk about: thermal phase noise, amplitude noise, systemic error, that is, and there is also thermal noise they talked about. All of them can actually impact what you can actually do it. So then you have to do correction. There are a lot of math goes there, a lot of computer programming goes into to be able to do it and to make this thing happen. So basically, then you have a synthetic data set. You look at blind image of, then objectively choose the image parameter and validate the image is correct. So the validating part is very important. That why it is validating and important, because you kind of know what a black hole looks like, but do you know exactly what it is going to be and how much is, let's say, the diameter of the black hole going to be, and especially when you have an error. So here, what you have to do, you want to test your ideas on something that you trust it. So for example, let's say you take you know me, and you know what I look like, and so I'm going to do something with, take a picture. Then he said, I can compare, said, yes, it's me or it's not you. I can look at it, computers can, even if I do a little bit of random changes, they will say, yep, that's deep, we know who he is. On the other hand, if it is a picture of a different person, if we do a computer imaging, you can say, no, this is not the same one, because if you have what is called a point of reference. If a point of reference is me, and I compare it to somebody else, you say, okay, this cannot be it. Similarly, if you show a picture of a cat next to me, no, you will know that it's not there. The problem with imaging the black hole is that we don't have a frame of reference. We don't have a picture of me to say this is what is going to be. So what they do is that they essentially do is that they create, they start with an image and they purposefully randomly create error on that image, and then the algorithm runs from the other end to say that, okay, I'm going to give you a bad image. Can you get it back to what the original image is like? That was the challenge and what they did actually. And I said, I did say about computer networks. So let me go to the computer network thing. So let's go to Frank again. I said, science, physics, and what I talked about. Why is computer network important and whatnot? So I'm trying to track of the time. I do not have a watch. I don't wear a watch. My phone is nowadays my watch. Anyway, Frank said that he was, Fermilab is in that University of Chicago, very well-known, named after Fermi, well-known scientist, that in 2001, he actually realized that why a local area network, you need to put computers together, quantum computers, so that you can do a large computer to make it basically like supercomputer, because he wanted to learn about something through the computational power. The power is important, but one computer did not have the power, enough power to, like your computer or a laptop, the power to do the whole thing, that you have to actually put things together to make it what is called a network, right? And so they did spend a couple of years commissioning the network, and then eventually they did a worldwide, and that eventually got to what happened in a much, much bigger thing in Switzerland, what happened. He made a very interesting comment, the second comment in the middle here. So I'm going to say that, when it become international, no one wasn't willing to write the check to one country who's going to host all the experiment on the data. So that's another thing, interesting thing that plays in there, that they wanted to distribute the country to invest, and instead, and the Switzerland is always a non-aligned country. Everybody likes it, and it's still even not part of United Nations, if you know. And so they said, okay, we'll be willing to do it kind of a neutral place to where we can do it, right? Good. Harvey actually, Newman, who I mentioned, by the way, Harvey's 70 years old. I've never seen somebody with so much energy when, excited about what he's doing and whatnot. And Harvey, I got to know only like 2 years ago. because I was in a meeting and related to computer networks. And I said that this person is here, he's from Caltech, he's a physicist. And I was scratching my head to see why is he here. And I got to know Harvey very well over the last 2 years. And they said that, in 1981, when I moved from CERN in Switzerland to the lab in Hamburg, and then he got back the job in Caltech, California Institute of Technology in California. Because back he was wondering how he could do the work when all my stuff is somewhere else. So he actually created the first international network for high energy physics, which I was not aware of. I know more about from a commercial network point of view, like the internet and but spatial network and stuff like that. I was not actually more aware of it as much until about a few years back. And ESNet stands for Energy Science Network. It's a big network now. They try to connect different places together to move data and whatnot. So you can think about like a specialized internet for the purpose of science data. So Harvey has a lot of contribution in that sense. Harvey shared with me this particular image of what the global data flow looks like. You can see CERN. So I'm going to get the pointer off. So CERN here they call it the tier 0. Then Paris, London, Chicago, those are tier 1. They have 100 gigabit per second links that's connected to those ones. Dedicated way to connect. And then there are tier 2. These are different centers around the world. And then you can go to different institute, that means academic institute. And then you have a workstation to go to the tier 4. They have actually structured it that way and what sort of things you get. So tier 1 is only real-time data processing. Tier 1 and tier 0, I mean. Tier 1 and tier 2 is data and simulation produced. Tier 2 and 3 also do data analysis. And this is where those who are interested in physics want to do data analysis. I'm going to show a site 1 second, and you can actually look into what actually is possible and whatnot. So it also talks about cloud, and anybody has a question later about cloud, I'll be happy to address that. So let's see. Good. This is the second picture is from Frank Wertfein. Frank gave me this picture, said this is where the global data science picture, where these are the location of storage and compute cluster where it is there, and they're connected by links, right? And you can see there are, of course, a lot of locations in Europe. That's why a lot of circles there. You see many locations in the US. You can see a location in South America, and obviously you can see the telescope location in Chile I mentioned to you earlier about. And there are a couple of slides in Africa here. You can go to, there's India, it's there. Then you've got a few in the Southeast Asia, Australia, Japan, and China. All of them are connected with the network to share the data, to do you can use the data, analyze the data to be able to actually generate new science. That's very, very important. So data plays a very important role. Networks plays a very important role so that you as a scientist can do different things, right? So here's a site if you want to make a note of it. If I don't, I will hopefully remember to actually put it in there in terms of what we have here. And so opendata.crncern.ch, you can go to this link. You can say it's explore more than 2 petabytes of data. This is available. It's an open data for particle physics. Anybody, anywhere in the world can actually use it. You can download smaller snippets if you want, and you can do something with it because you're interested to know something about particle physics. So I want to quickly talk about a couple of, because I've been talking mostly physics here, but you realize that the idea about data and the network become actually much bigger than just the physics problem. Here's an example of digital pathology. FDA stands for Food and Drug Administration in the US. They allowed the marking of what is called the whole slide image that actually as a digital image you're going to allow it. They're going to do that. Until now, it was all analog on a microfilm and stuff like that. So it has it has lots of pixels. I can see that, right? So you can see that one image is actually 5 to 6 gigabyte. Remember, I talk about megabyte, I talk about terabyte to the megabyte to the gigabyte is 1,000 megabytes makes it a gigabyte. So this is the idea of where it is. There, when the Memorial Sloan Kettering Center is in New York City, they alone have generated over 1 million whole slide images. So if you look at the 1 million of this thing, and this is now you're getting to the petabytes of image they have. So if somebody else somewhere else want to learn about something about a pathological issue, how are they going to be able to access it? Because each image is going to take more time. So that's important to be able to figure it out. So a couple of more examples, more science examples. Polar geospatial data, very important, a lot of data there. My colleagues at my university work on biomaterials. They use a confocal and multiphoton microscope. Each of the images is actually 10 gigabytes. So they are struggling with how can they the image they created, make it available to others who want to learn or investigate that information. Our human DNA, if you actually look at the entire DNA, one person's DNA is 1.5 gigabytes. So now if I say that, okay, what is it, 8 billion people in this world, right? If you multiply 8 billion by 1.5 gigabyte, you suddenly realize, if we are actually able to collect everybody's DNA, that it is almost impossible to store everything in one place. So that's a huge challenge. So future medical discoveries where you are going to process about the DNA related information. And there also we face some sort of an error because of a different way of approximate. First, we cannot have everybody's DNA for a variety of reasons. So we have to sample it. Maybe you sample 100 people's DNA, right? And based on that, you might be able to say, okay, somebody has a cancer or not cancer. Right now, even with the DNA that they talked about for paternity testing and all this stuff, they're not looking at the whole DNA. Only a part of the DNA they know is good enough to be able to capture it to test that information. That means you're not looking at a lot of information we don't even know what it is, right? So if you think about our facial feature, what we look like, we don't need to look at the whole DNA. You look at only one part of the genome and compare with somebody and say, okay, this is how much it is matching and stuff like that, right? So these are all different examples. So basically what all of these things is going is that we're going to what is called the data intensive science, okay? So the data intensive science is basically the data is becoming, doesn't matter. I mean, I only gave example from physics. I gave an example from geosciences with the polar data. I gave example from biology with the DNA information, chemistry, molecular information and stuff like that. You can you think about biomedical engineering, all of them, the data is becoming bigger and bigger and bigger, and that impacts what and how we can do science. And this is where the network becomes very important. So I'm going to finish it off with giving a little bit of idea about why computer network, even with the internet that we have, and our specialized network for sciences we can construct, that there are always challenges that we have not been able to, that we can actually have new things to look into to make it improvement. So the first thing is that the job of as I said at the bottom of here, what's the job of a computer network? Move data faster. From point A, you want to go to point B, you're going to move it as fast as possible. And so moving data fast doesn't mean that, as easy as it sounds actually, honestly, believe it or not. Why is that? So it goes to something called what is called is in computer network is a governing principle. It's called a bandwidth delay product. Product means multiplication. Bandwidth and delay means those are the two different terms. So if you multiply the bandwidth, which is really the data rate, and multiply by the delay, what you get is the product, which is actually in networking terminology, we use the word window or TCP window because the protocol is known as the TCP protocol. But in terms of the unit, it's basically byte. So if you look at how much data rate I can do and how long it takes to bring it, if you multiply those two times, you get the byte in terms of the, okay, is it 5 megabytes or 2 megabytes or 64 kilobytes and whatnot. And so this window is what sits on your computer, on your phone, because your phone also uses TCP protocol when you're trying to access something, access a website and whatnot. And so the phone, obviously what you are doing, your phone might have a, I don't know, I have 128 gigabyte of memory on my phone now, but it cannot use all of it for the purpose of TCP window, because you have all the other thing you are storing, all your pictures, your selfies, your software you are doing. So you have to allocate only a small part for the window. So let's change the calculation, change the order of the thing. I said the maximum window size is bandwidth times the round trip. So if I divide maximum window size, which is in byte, by round trip time delay, I get the bandwidth or the data rate. So this is, by the way, this data rate is what is called the theoretical maximum. So if I say that my window is going to be, let's say, 1 megabyte, that's the window my computer is going to allow you to take data at a time in terms of what we call it, a group of data we get it in a time. And then if you divide it where I'm trying to get the data from, the round trip time, you divide it, that's your rate. That's what it's. I'm going to show you numbers in a second. You'll see what happened. Second important thing I want to point it out, the TCP, the protocol I talked about, can actually never reach the data rate given these two numbers. It will only get maximum of about 75% of this value. So what I'm going to show you is like a theoretical maximum of the data rate you get in terms of what you have it, right? So that's what I mentioned it here, and let's look at it. So a little bit more basics about computer networks here. So data flow, so anytime you have a large, like a web page you want to download, you get a picture from a friend, what it is, it actually does, picture could be in megabytes, or, it could be kilobytes in the smaller file. But what it does, it breaks into smaller chunks, which we, in a computer networking terminology, we call it packet, if it is in general, but we also use the terminology segment because of the TCP that I mentioned earlier. And the interesting, each packet is sent independently. So you get a file, maybe an image, you break it into small packets, and you're going to send it through the network. Basically, shoot it through the network to get to the other side. So I have a small animation here. Let's see if it's going to work. So here is in the old days, I used to say send email to grandma. You want to send something. So here is something, image, email, or a image you want to picture. You break it up into 3 packets here, 1, 2, 3, and they can go through like a road network through different ways. Like those blue points are routers, or road network. You can think of like a traffic light. So you get to a traffic light, you can take a turn this way or that way. But they have an address that takes you to where you want to go to the destination. But what happens is that when you reach to the other end, it doesn't mean that they're going to necessarily arrive in the order I sent, 1, 2, 3, those packets. They may arrive in 2, 3, 1, because they went different ways through the network to reach them. So this is like saying that you are going to visit your mother or parents, and all of your siblings started in one place. Each one is driving a different car, but you are going to go different ways. Although you started one after another, you may not arrive exactly at the same time because you took a different road based on the traffic condition and whatnot. So one thing your computer, your phone is doing all the time is that when it gets that thing, immediately puts the packet together to put it in the sequence, reassemble it, and that's the one you're actually going to see it. So it has to do a little bit of work. But the idea about breaking was very important because it allows you to send the big thing into so smaller pieces to send it, right? That's great. So now let's talk about the window size, the latency, and the data rate. So I have put some numbers here. It's a simple calculation from the formula I showed it before. If you have a window of 0.066, which is in megabytes here, I purposefully did it here. And 0.066 happens to be 64 kilobyte, which is in actual term is 65,536 because it's 2 to the power 16. Because you use 16 bits of TCP window field to say how many you can pump, how many bytes you can pump at a time, pumping it, right? Most laptops, when I started on computer network on the old days in the computer, our Windows, I remember our Windows used to be 512 bytes 30 years back, first implementation on the thing. That window, they have to keep making bigger and bigger because people are sending more thing. And remember what I said earlier, because that is in the numerator and divide by the delay, that's going to limit how much you can pump it. So you want to make it bigger, okay? But making it bigger is not easy as you might seem, okay? So here's an example. Theoretically, I said that, let's say my delay is 100 millisecond, and say my window size is 64 kilobit. So you take the window size, divide by delay, calculate it back. What you find from the bandwidth delay product is that your maximum data rate is going to be 0.005 gigabit per second. You got it? It's not even 1 gigabit per second with a 64 kilobyte window. Suppose I have a link, 100 gigabit per second link. What happens is my link is going to stay, you are the only one driving. Think about like driving, right? It's like saying that it is creating a speed limit, although I can go faster because the link is faster, but I cannot use the link because my window is the limiting point, one term. The second term is the latency is the limiting point. Latency, you cannot do a lot. I'll come to that in a second, but let's only increase because it's in the numerator, I'm going to increase that value. I multiply by 10 times more. Let's say I make the window size 6.5 megabit. What will happen here? I can get to half a gigabit per second data rate I can get for a file, but I have a 100 gigabit link. It's not even using 0.5%. It's just sitting idle, which means that I need to keep increasing the window size. By the way, 65 megabyte is very light. No general computers have a 65 megabit of TCP windows. I'm just telling you, your phone doesn't have it, okay, as an example. So this might be a small homework for you. You can search and find out what the TCP window size for different computers are. And when you go to even bigger, 655 megabit per second, megabytes, I mean, of window size, I can only get to 52 gigabit per second. Only half of the link will be filled up. So this is now one big problem on the computer for big data intensive science. How do I make a computer that can actually do a lot of large memory? It's not written in disk, by the way. This is in memory. It stays in memory so that it can do memory management very, very, very well, so that it doesn't become a bottleneck. There's how do I shuffle it through, and all kinds of interesting questions that comes from a computer architecture point of view, from a computer to be able to actually support the fast data transfer. So I'll skip the TCP scaling window. I gave you some other information here. I'm going to skip it. One thing you can say, remember, I have not touched the latency. Suppose I can somehow reduce the latency by 1/10. What's the good thing about it? That means it's in the denominator, right? That means I can make it faster, even if my window size is smaller. So if you look at this 65 megabyte and this one reducing it, I can actually make this 5.1 go to 52. You got it? And so let me go back to the color again of pen. And so you can see that I have, I have this data rate. I can go to 52 because I reduce the latency. I'm not saying I can do the changing, but simple numbers can help you to understand what is going on. And then if I can have here, I can reduce it. This is one when I go from 52 I can go to 524 gigabit. And this is the first time I hit the limit of the speed, because I have more data I can actually pump, because on the both I change the latency, the round trip delay, and the TCP window, that now my link is the bottleneck, right? All right, so you got that, right? So this is a challenge we're facing right now with the computer network. So I did a global ping earlier this evening before I did. You can go to this link to see how much is the delay between different places in the world. They do some measurements periodically and then report it. Okay, so here's the picture I collected, and I purposefully picked two places. I could not ping any place in Assam. So I pick New Delhi. You can see New Delhi here on the top here. and you can see Kansas City here, and you can see that the value is about 237 milliseconds. So remember, all my numbers, I showed it by 100, with 100, and actually more than that, it is going to, is twice, 2.5 times more roughly what it is. If you are closer, because of the network, you can see it is less. Look at Barcelona and Amsterdam, they're closer by, it's only 31 milliseconds. So the physical distance matter, because eventually, remember I talk about fiber optic, fiber optic that connects the internet on the largest international scale. They have to go, and besides other delays happens and whatnot, because of the switching and all this stuff, that there's a physical limit to how smaller that we can make it, which means that since I cannot make the delay smaller, and by the way, this is important, I'm again putting the formula where, since I cannot make this round trip delay too much smaller, only thing I can play with is the window size. I have to make somehow that window bigger. And this is a very big challenge on the computer itself to be able to do. So that's one example of the challenge we face with, that we need to be able to solve better, so that actually we can push more data through the network for data intensive sciences. Good. I go back to my table again. Now look at the size of a file. I put a 1 gigabit file. It is going to take, if you do the initial 64 kilobyte TCP window 100, it's going to take you 25 minutes to transfer it. That's a long time. Remember what I said about the digital pathology? Each image was 5 to 10 gigabytes. If I go at this window level, it's going to take 254 just to take one picture to download it, because I'm not being able to speed the link speed. So of course you can increase the window size and cut it down. You can do it. So only if your computers can do it, only some computers can do it. Not everybody can do at the high end for these values here, right? So I kind of gave you an idea about the file size, what happens. And then what I do is there's another, you can now say that if I go to petabyte, talk about, even with 65 meg of this thing, very low latency, which is not possible right now unless you're in the same room. Even sometime in the same room, when I ping my computer, it takes me more time, right? And so your time to transfer is a big number right now. We have big challenges. Luckily, all of the data created on for different sciences is not one large file. It's different files, but sometimes they want to transfer a lot of files together. So there are other techniques being developed right now to transfer a lot of files together so that you can make this thing. So one last thing I want to talk about, I'm about to stop it right now. Sorry, I went a little longer. Then I have time for Q&A, and happy to answer any questions you have, right? So new factor is what is called a transfer is a checksum. So we actually get when you send a packet, because of that, there's always some error in the link. You actually can drop some of the, you change the bits information. So 1 becomes 0, 0 becomes 1. So what we do is that from one point to the next switch, we actually correct it again, because this is called a CRC correction. So CRC is very good, 10 to the power negative 16, which is great for small files and stuff like that. Now, if you go to gigabyte file transfer, you can see that I can have the best situation, maybe 100 of them I will get undetected, the packet. It'll say it is correct, but you could have 62,000 packet that is going to be corrected. So somebody raising a hand, let me see. Do you have a question? You can unmute yourself and ask a question. Did you have a question you want to ask?
Thank you.
So I'm almost done, but somebody had a question. Yeah. So maybe I'll wait till the end of it, then answer the questions. Just a second. Only a couple of more pictures. So this error is something we're trying to figure out with new network technology. I'll skip it. It's called in-network storage and computing. I'm actually managing this project at my National Science Foundation. It's a $20 million project. They're setting up a 1 terabyte per second link connecting different places. We're expecting international connection with that. And so that's sort of where we are with all the different things. And so, and a lot of interesting thing happening. So as I said, the basic knowledge is very, very important. So you wanted to know about basic physics, basic statistics, computer science, basic chemistry is important. I'm not saying you need to know all of this stuff, but the fundamentals are important. Basic economics and social sciences are also very, very important. And then always focus on the fundamental. You know, remember, I look at just simple numbers to understand what is happening with that, what is going on, right? And you just play with numbers and get an idea. Numbers give you insight. Analytical thinking is very important. You know, that you actually, some of us are a little bit better than others, but you can look at different problems, think about number, question why the numbers are coming out the way it is, and going to make you sharper to think about it. And one other thing is that writing is very, very important. So you wanted to be able to, you want to write your ideas. It actually, writing ideas help to sharpen the way you think and whatnot. So as I said, science is very interesting and exciting right now. It's going to a very interdisciplinary nature, a basic knowledge of basic fields, and talking to your friend from even at the college or higher secondary level. Different people are stronger in one subject against another one. I have learned that way many things in my life, and that has helped me even to these days. I'm grateful to all my friends because of that. But it allows you to think a problem in broadly and whatnot. And eventually I saw that common sense, imagination, and curiosity are really, really actually useful to be able to do what you want to do. So I will finish with two quotes here, one from Einstein. Einstein said, logic will take you from A to B, but imagination will take you everywhere. And the second one is that Tolkien's quote from his book. He said, not all those who wander are lost. Thank you. So I'm going to stop it here so we can open up for question and answer. You can, I'm going to go, let's see. Probably the best thing will be that I am going to stop sharing the, give me a second, automatic. I stop sharing the screen and I will go to Dan. So let's see. Okay, now we are going to ask, let me do one thing first is that I'm going to read a couple of the questions I just saw.
Thank you.
Thank you very much. Okay, all right. So questions I'm going to, I'm sorry, go ahead.
Most of it was on my head. Thank you anyway.
Okay, thank you.
I like the earlier part. Thank you.
Okay. All right, so let me read the first question I saw. Could you describe about, it's from Bijoy Lakshmi Borua. Could you describe about the web-like topology of cosmic web structure and why do the cluster and supercluster tend to fall into, this is going to, I think the question is, if you are, if you can, I think you should be able to unmute yourself. Let me see. So you can, okay. Can you unmute yourself? Okay. So I think this was a question about the animation at the beginning when it dropped into, am I right? Vijaya Lakshmi? I cannot hear you. I will assume that that's the question. So what happened is that they are drawing the grid to give you some idea about how the lights go in parallel. Lights go in straight line, first thing we know, right? So if I have two sources of light going here and another one, they do not cross. So they're just drawing the grid to show that these are arrays, the lights are going in parallel. And then when you have a black hole, you actually drop into this sort of a situation where, because it's not like a planar view of looking at it, you're going to drop it. So you are going to, the light is going to take a curve. So if it's going to take a curve, it's going to take a like almost like a web type structure that you are talking about. So this is only a kind of a pictorial view of what it is. And I don't know if I answered your question, but um, if you can speak, if I can hear you, I can try to clarify that question.
Yeah. Hello.
I cannot. Sorry, I cannot hear what you're. If you, if I, maybe you can type it again. Let me read the second question. So, what are the chances that LHC accidentally produced a black hole? No, the LHC cannot produce a black hole. LHC is only, remember, Large Hadron Collider is only trying to capture particles that we don't know, and we do not know about. I want to clarify about the black hole. Black hole is, think about slightly differently right now. So we are in the sun is in the middle, all the planets are going around. When the sun eventually going to lose power, basically, it's going to, the gravitational, forces, you're going to basically collapse into what is called a black hole. So because sun has plenty of power right now, it is not going to have the situation that we are talking about. And for that matter, LHC cannot produce a black hole in itself. LHC's job is only being able to capture things that we do not know about. Very, very good question. It's what was a question from Mohit Kumar Sah. So I answered that question. Any other question? You can unmute yourself and ask question. You can ask in Word, and if you want to just say, I have a question, type it in. I will call your name also. I can see your name. So. Okay, anybody else have a question? Okay, I'm going to kind of talk through a couple of questions. My sister asked me a question about, give an example of, I talked about error in the measurement with the black hole. And so I'll talk about how, that error can happen in other areas as well. So one example is that when you do the elections, you take a poll, and that when you take a poll of people and you say that one party has got a whatever percentage of vote likely to get, it is not as a humanly possible for us to poll everybody, ask everybody opinion. So what we do is that we do some kind of a random sampling or stratified sampling. We do ask only let maybe 100,000 people or 10,000 people their opinion with which party they are going to vote for, right? And based on that, because I only could do the 1,000 to 10,000 people range, in a country like India, where we have over 1 billion population, it is only an approximate you have an approximate source of information. So when you have approximate source of information with only 1,000 people or 10,000 people, you are going to have an error, and you have to give some quantification of how much error it is. So usually with a poll, what you find out is that it may say one party gets 55% vote. And so if you have a 55% vote, so what happens with there is that usually they give what is called a margin of error. So margin of error could be from few percentage, 3 to 4%. So let's say it says 5%, one party got 55%. So you can say, basically what we can say with confidence, we can say the party may go all the way down to 45 or 50 or 60. Within that range, the actual number is. It's not the average number in the middle. It's only average number. The window is actually error margin. It can be very, very large, 3 to 4%. So that's an example of what it is. So, with measurement of any type of things you do, even like a physics experiment you do in your 11th and 12th grade, you can actually find out what you can actually do. Take 3 measurements. I remember when I did physics experiment in class 11, we said, oh, they said the measurement error, just take 3 measurements, you'll be fine. But it didn't say that, the error, how big is the error? We didn't discuss that because we didn't have enough of a statistical confidence interval idea at that point and whatnot. But that idea of measuring multiple times of something is very important. The same thing like saying that you drive from point A to point B. In the morning, it may take you, I don't know, 1 hour, afternoon, maybe 30 minutes, at night, maybe 15 minutes because there's no traffic. If somebody asks you how long it is going to take you, either you can pick one of those 3 numbers or you can do an average saying that, okay, my average is, on average, this is how long it is taking. By the way, I have an error margin because it can actually swing up and down. So when I go to Assam and I have a honorary appointment at IIT Guwahati. I usually I get a person who drives me to go back to the city. I ask him that how long it is going to take me from the, it's my favorite question to ask a driver, how long it is going to take me from the IIT campus at that point to get to the Guwahati. I'm always very impressed with people. This guy, the driver who's talking to me, I always talk to him and then he'll say that, I cannot tell you, because I have no idea, because it depends on what it is happening that I cannot see. I don't know 10 minutes from now if there's an accident or what it is. That's actually, in a sense, the very, very, very good answer, right? Because you don't know the answer really. The other way you can say that you can collect some data. I said, okay, I make notebook, I write it down. Today it took me 10 minutes. Another day took me 30 minutes. Another day, 1 hour. You write down what time. You can then look at those numbers to say, okay, do I see some sort of a pattern at different time of the day to give you some information about it. Okay, that was my long answer on the question. Okay, second question is, how come black holes are so powerful that it absorbs everything, even as strong and powerful as, so that's a very, very good question. Maybe my knowledge of physics is limited to be able to give a very good answer on that one. Hopefully somebody with a good physics knowledge can actually give that answer to you. The next question is, will it be helpful to study data using quantum computer? Can we use quantum quantum entanglement for sharing data? Very good question. This question is by Wahidur. The previous one on the black hole was on the powerful was by Ria Nayak. Thank you for asking the question. Let me answer Wahidur's question. I'm so glad you asked the question about quantum computer, because that's one thing we are struggling right now. Can you build a quantum computer? Right now, building a quantum computer is very difficult. I mean, it can be done. It depends on something you call a qubits. Qubits are, you can only construct only about 50 qubits. We're at a infancy of being able to do quantum computer, okay? But quantum computer is going to change everything that as we know it. That's first thing. Second thing, because you asked this question, it goes to quantum networks. Because if we can create quantum network, then we can think about quantum networks. Sorry, quantum computer, we can think about quantum networks. No quantum networks exist today. We only know about internet and all the spatial data network, use a similar protocol like internet to do it. Quantum network is way, it's not even, we are only imagination right now. It's like the Higgs boson we talked about in 1964, right? So maybe it is going to happen in the next 20, 30 years, and then we can actually get to be able to do that answer, get there. So yes, quantum is going to change it. everything drastically? Will it help tomorrow morning? No, it's because nothing exists there. But is it going to happen in the future? In the next 30, 40 years, it's 20, 30 years, it's going to change. So, it's a very, very good question. The next question is from Vikrant Reddy. He has a question on what is the size of an Event Horizon Telescope? So Event Horizon Telescope, if you remember my slide at the beginning, is that it's in multiple locations. Okay, one in Spain, one in Chile, one in Mexico, in Hawaii, like that. And so each one, the aperture, I forgot the aperture. It was actually really, really, the aperture is pretty big. The disk is big, means very big in terms of the size of a human being, like you and me, okay? Because that basically is, I'm trying to figure out, I don't want to give you a wrong information here. Just give me a telescope. Okay, if they have a, yes, it is actually, I cannot figure it out right now. Very good question, but I will. But it's actually very, very large. It's not. It's large means in many buildings you put it together. Think about like that. Disk is like like this, but not in the way I can show it in my hand. It's much bigger than that. So because you want to be able to look at too far out. Remember I talked about the aperture. So you have to have it very, very large to be able to do that. The next question is from again Mohit Kumar Shah. It said that you discuss about TCP and its limitation in increasing window size. So are scientists trying to invent new protocol for faster data transmission? The answer is yes. We are always looking to do faster data transmission. I already talked about the window size. By window size, you can address a few issues. But if you remember towards the end, I had a slide on a fabric testbed. I talked about it's a next generation testbed. It has an idea called, we're using an approach called in-network computing and storage. Okay, so if it is an in-network computing and storage, with that, what you can do, you actually can do a different way to create a protocol, which is going to be like, you do it in staging ways to be able to. I had a slide earlier that we believe is going to actually take you to take more bigger. Even in TCP, there are still research going on because many variations of TCP exist nowadays. It has changed in the last 30 years. You may not even realize your computer is uploaded with, a new version of the computer has a new TCP version. Most computers like Linux machine nowadays has a cubic TCP. So it gets, automatically as you operating systems are upgraded, it automatically gets the latest version of the TCP with the different parameters and stuff like that. So research obviously is done, and that can take you to the next part of what you are trying to answer it, address it. Hopefully I answered that question. Okay, let's see. Okay, the Rima Das has a question. Does quantum entanglement share data faster than the speed of light? Wow, this is a fascinating question. So far we believe that speed of light is the ultimate, right? With quantum, especially with getting to the particle or things we do not know about, maybe what we say is that it is going to break the barrier about what we know about light or what it is. And that's a very good question. I wish I had a good answer for that one. The next question is from Wahidur again. Is there another technology to send data faster than fiber optic in use? Not really. Oh, sorry. There are what I call is a workaround. So what you can think about is that think about like a road, so let's say I have a road with 3 lanes in it, all parallel. What I can do is that, and then you can think about those 3 as a 3 different fiber optic cable. What you have to do, you can break the data first and then ship it out on each of them at the same time, different parts of the data. And then you have to receive it on the other end and piece it together, okay? But so if you can do this sort of a parallel way to sending it the data, you can get more data rate than what a single fiber or single physical link can give you. But this also means that you have to have the equipment at the other end to be able to take care of that, breaking it up in a different ways to be able to piece it together and piecing it together. Very, very good question. Okay, I will wait for another 2 or 3 minutes and then I will stop this session. So we're at an hour and a half time frame. So, and somebody, if anybody want to ask question, so directly by voice also, that is okay. So unmute yourself and ask it. So. Okay, if not, we're going to stop the session. Thank you for joining it. And especially I can see at the end, we still have 37 participants. That's very nice of you to join, stay all the way to the end. And I know some of them were my family members also who stayed until the end. So, oh, okay. So there is a couple of more questions that just came in right now. Okay, Mohit Kumar Saha asked a question. Can you briefly discuss about your PhD in computer science, what you studied? And okay, so my PhD in computer science is, I completed PhD in 1987. That's 33 years ago. So Mohit, I can see you on the video right now on yourself on the screen. So I did actually do a very interesting, I work on a optimizing, breaking up data into, sending it into different parts, and trying to work it between different computers. At that time, we had only 20 computers. We're trying to connect it with a network. And I was optimizing an algorithm, how I can parallelly optimize that data. So this is 1985, 87 to 87 period when I work on that. So that's what my PhD in computer. But I got interested in network because I was working on the optimization algorithm and algorithms and parallel computing at that time. And then I went to work at the AT&T Bell Laboratories. That's when I really got interested in networking. So I was, so essentially you can say that I changed my field from what I did my PhD in over time. And so, so that's an example of what I actually have done it. So, okay, so Ankita Saha, very informative. We'd love to get the opportunity in future to listen to you again, if possible, work with you. All right, sure. I am planning to do a few sessions. I might do actually a little bit more detailed talk on computer networks that I could not do it today. More information, more on the protocol part of it, and that I can make it more interactive also. But also I'm going to do a separate talk on routing, and I have different ideas, but I'll probably schedule it every 3-4 weeks, to try to do it. And please stay on the WhatsApp group, the Deep Medhi webinar group I created, because that's where I'm going to announce the future talks in there first. Okay. So I did that. Thank you. Something very informative. Okay, so Rima Das. Another question from Rima Das. Since mass is curved, sometimes space their mass is heavier than the sun. This is a very interesting question, right? So if something gets heavier, that we do not know. That's the mystery of nature that we are trying to figure it out, right? You are asking a fantastic question. You should talk to some physicists, Rima Das. It's a fantastic question. Hopefully somebody can help you. If not, if you got my email, remind me to remember to write me an email later, so I'll find out somebody who is an expert that can answer your question. All right, very good question. Thank you. All right, that's basically what it is. Anybody has any other question? You can ask by voice.
Debuda, I have a question for you.
Oh, okay. Go ahead.
I have a question for you.
Okay.
Yes, sir, you are from Dunyajan. Acha, we want to put gigabyte, megabyte, then gigabyte. Petabyte is a new one, no? I'm not very clear about it.
So
CPI understood, TCP I understood. Ria, like my PhD student is also there. Ria, you can ask. My brother is from US, he's calling. So you think over, first let him explain mine. Okay.
Okay, so you know the gigabyte, that gigabyte you know about, right? So 1000 gigabyte makes it 1 terabyte, 1000. Okay, then 1000 terabyte makes it a petabyte. You got it? So that means 1000 and times 1000 is 10 to the power 6. You multiply gigabyte by 10 to the power 6 is going to make it a petabyte. So that's how big a petabyte it is, right? And then there is even bigger things called exabyte and whatnot. Yeah. Okay.
Yeah.
By the way, thank you for all the people who said thank you to me. You are sending me a lot of messages. I will save all of the messages for future and whatnot. Anybody else have any other question? I will hang around for another 2-3 minutes.
Yeah, do you have any question? Yeah, and Nayak, my PhD students from the Legend. Do you have any question? Or Buddha, do you have any question? PC Medhi? Where is Hoi Prasad Medhi? Buddha, Bhanti Behi?
He might have dropped off. That's okay.
Ria Nayak, do you have to ask anyone? Otherwise, he'll wind up after some time.
All right. Okay, if that's it, then I'm going to close it. First, I'm going to stop the recording. So let me